Hi, and welcome to my channel, JaberTime. Today I'm going to talk about partial derivatives. As you could see from the graphs that I have, we're going to go over it in detail, each one of them. On the coming section, we're going to talk about tangent planes. What I'm trying to say is, this will be kind of like introduction to the coming video. So you need this for also the coming video, tangent planes. I could put them all in one, but let's keep it this way to the best that I can. I don't want to make my videos 45 minutes. I'll try my best to minimize the time as much as I can. And that's why I write the graphs, or I do the graphs and I do write my notes ahead of time. Let's get into it. Now here, partial derivatives, we're going to describe f of x and y as a function of two variables. We're gonna, for now, consider x that is the variable and y is a fixed value. Let's call it y equals b at certain amount b. G of x will be f of x b. Now, my new function, it's a function of x. It's not a function of x and y anymore. It's modified to be f of x b. b is replacing y, so y is not changing. G prime of a, or at a, will be the first derivative with respect to x, because x is my variable, it's not y anymore, at the point ab. Even though I'm writing here a, it's still at ab. The partial derivative of f with respect to x at ab. Formally, as a formula, this is how it looks like. G prime at a will be the limit as g of a plus h. You could see that a is the one that is moving. I'm using g now over the difference h, which is the same like from calculus 1. But here's when you put the two elements in it, which is ab. Notice that a is the one that changes and b is still b right here and here. So the focus is we are moving from a to a plus h with a difference of h, and that is my delta x. In previous math we used to call it delta x. Now, for now, it's delta x, but when it comes to the y part, it's not going to be called delta x. In short, formally would be better to call it h as a small difference between a and a plus h. Same way, if you have x to be fixed, not y to be fixed, then we're going to call x equals a. We're going to fix it at that value a, and we're going to make y the variable. To distinguish between this function, then modify the new one with the name g of x, we wrote here capital G of y, because it's not the same. And we don't want to just call it g as like small g. So this function would be a function of f. Instead of x and y, it's a and y. A is fixed. A lot of details, but it's so simple once you go back and look at it. F derivative with respect to y, because x is fixed, y is the one that changes, will be same style, same format. Look at a is not moving. I have b plus h as the new value for the y component, and the original value was b. So we're going from b to b plus h, and that's my difference right there. It's exactly like calculus 1, but from a three-dimension point of view, because we are actually in space. In 3-dimension, we're not on the xy plane. If f is a function of two variables, the partial derivatives are the functions fx and fy, or f sub x and f sub y. This is the formal way with colors to make my notes clear, so you could see and copy or whatever you want. I don't want to write them down and take your time. Just take a look and see that f of x focuses on x and y is not changed. Y here, you keep it y right there. On the other hand, x changes, this x changes. Here, the y changes. You could see y and y plus h. So my function z is f of xy, and this is a lot of different ways of writing the first derivative with respect to x and the first derivative with respect to y. Just take a look at them. If I read them quickly, it's not practical, but as you could see, the famous ones will be like a shortcut f with the index x. Sometimes we call it f1. Sometimes we call it d1, or capital D like derivative of f with respect to x, and so on. You know these guys too. Same thing applies to the y part. Here's an example that they want me to find fx, first derivative with respect to x, at 2, 1. So if I say it fx and fy, that's kind of like to go faster. It's the first derivative of f with respect to x. Now here is just a practical example, just to practice, nothing more. Looking at this, finding derivative with respect to x, x cubed becomes 3x to the second. Now when you come to this term, this is a constant to me. The 2 is going to go down up front. So it's going to be 2xy to the third. And this is a constant to me, so the derivative of this will be 0. That's if I'm going with fx. Now, finding the derivative with respect to y. Okay, let's go back here. Once you have it, to reduce the time and save some time, just plug in 2 and 1. 2 for x, 2 for x, 1 for y, and simplify, it's 16. So the first one is done. Let's go over the second one. It says the derivative with respect to y is the following. Let's just verify. What's the derivative of this with respect to y, knowing that we are keeping x as a constant? 0. What's the derivative of this, knowing that y is the variable? So x squared is the constant. You bring 3 up front, and this becomes 2, and that's what we have. What's the derivative of this with respect to y? It's going to be minus 4y to the first. One more time, 2 and 1, just plug it in. 2 for x, whenever you see x. 1 for y, and finish it, which is 8. Meanings of the partial derivatives in 3 dimensions. You have a surface up here, and we are looking down at the xy plane. This point right here, down here, will be in 3 coordinates if you want it, as a, b, and 0. 0 for z value. Straight up, when you reach the surface, it's a, b, c. C1 is, in red, is the graph of the function g of x equals f of xb. Take a look at this. Y is fixed to bb. X varies. Well, that is clear. Let me go back to the graph and explain that. If you are on the surface right here, that's called z equals f of xy. As x changes, increases, and y increases, you are moving this way on it. As x increases more than y, you are moving this way. As y increases more than x, you are moving more towards this way. But what about I say don't change the y? That's b equals y. So if b is 7, you have to be to the right from the z-axis, if you call it that way, at 7, and you have to stay there. Staying that level, y equals b or 7, on the surface, because the surface is not a horizontal plane. Usually it's a surface. It's like a wave, goes up and down. So C1 is actually the trace of what is this. Instead of going all the way on the surface, if you wanna be on this curve, which is a trace of the surface, aligned with y, or having y equals b as fixed, that's gonna be a curve that is marked on the surface. It's like you're walking with the x, going, like, say, if x is like, let's say, north, you're going north all the time. You're going north and south. That's it. So that is the meaning of the partial derivative. C1 is your original function, but y is fixed. The slope of its tangent, look at that green one. If you want the slope of the tangent, T1, at this particular point, all what you need to do is what? Take G prime, which we did a practice one earlier in a previous slide, and plug in A. Which A? The A that they give you. That's it. That's the first derivative with x. Look, you're walking this way. That means you are having x values and y does not vary. Y is fixed. So your slope will be in terms of x. Your derivative will be in terms of x. And that's what you have. If you want it at a specific point, you just plug in the numbers and you'll be fine. Now looking at C2, which comes from having x to be fixed at A. Okay, let me try again. Now C2 will occur when x equals A. So when you go out to x equals A and stay right there, instead of being on the surface everywhere, you're going to have to be leveled with x equals A. So this is the curve C2. As a projection down in the xy plane, it's going to be actually this line right here, x equals A. Because you're not moving closer to the y or far away from the y. You're staying fixed at x equals A. So C2 is the curve. C2 is the graph of the function capital G of y, because you're moving this way. You're moving this way on top. That means your y varies, but your x is fixed. So it's called G of y. F of A comma y. X is fixed to be A, and the y component changes. The slope of the tangent T2 at ABC, this point right there, which is the projection down here, is going to be AB0, is G prime at B, which is the first derivative with respect to y, because as you go this way, your y changes. You're kind of like being graphed as a curve. Imagine this is the whiteboard, but normally it's called x and y, and now it's called y and z. And this curve is not on the whiteboard. It's kind of like away from the whiteboard within, let's say, a units. That's how you might want to look at it. It's a curve the way we see curves on the plane, xy plane, but today it's called yz plane. But it's not actually on the whiteboard itself. It's outside of the whiteboard that much. Okay, so just imagine it's aligned with this plane yz, and it's a parabola. Well, at least for now, it looks like a parabola. The slope of its tangent will be the first derivative with respect to y. Partial derivatives are rates of change. If z is f of xy, then dz dx will be the rate of change of z with respect to x when y is fixed. It's almost like calculus 1, but calculus 1 keeps you focused on x and y plane. Now I'm looking at the whole picture in 3-dimension, and I'm kind of like slicing it to be looked at as 2-dimension. One time I'm looking at it as x z plane, and one time I'm looking at it as y z plane. Let's take a look. This is when y is fixed, so you are actually going with the x z plane. Y is fixed, so z and x will change. dz dx is your slope, but you are on a curve that is outside the xz plane in 3D. sticking out with the y value when y is, let's say, b. dz dy will be the rate of change of z with respect to y when x is fixed. So when x is fixed, you're actually moved on the x-axis, let's say a units, and you stay right there. So it's going to end up as a curve, and you're going to find it's a slope, but it's like aligned with the yz plane, but out of it a units in the x direction. Now we have f of xy equals 4 minus x to the second minus 2y to the second, and we need to find the first derivative with respect to x at 1, 1. 1, 1 is down right here, or you could see it as 1, 1, 0 for z, because it's down on the xy plane, the z value is 0. If you plug in the 1, 1 in the xy, you get 1 for the z value. There is a lot to talk about on the graph right here. So let's move on, read the comments, and I'll go over the graph with you. The graph of f is the paraboloid z equals 4 minus x to the second minus 2y to the second. Imagine if this is like y equals 4 minus x to the second. You know, it's a parabola that opens down, shifted up 4 units. But it has 2 dimensions on x and y. And now with the z, it's 3 dimensions. So it's a graph like a parabola in 3 dimensions, shifted all the way up to 4. That is clearly from here. You could move everything to the left and call it z plus x squared plus 2y squared equals 4, and find the x-intercept and the y-intercept. I've done them for you. It shows right here at 2, and it shows on the y at square root of 2. So if you notice, square root of 2 is like less than 2, this much is less than this much, and 4 is higher than as a scale compared to 2. Which says also, if you ignore the 4 and you look at it, this is a normal opening of a parabola. When you have a 2 in front, that is going to speed up the y values, which means when you go with y this way, it's narrower, and when you go with x, it's normal opening, let's say, if you want to call it that way. So once you find the slope going this way or finding this way, you're not going to have the same slope at the same point. That's another point why you have different slopes. So the first derivative with respect to x of my z is the following. With respect to x, this is 0. With respect to x, this is minus 2x. With respect to x, this is 0. Now plug in 1, 1 because I was giving 1, 1. There is no y here. Just take care of the 1 for the x, and that's a minus 2. What does that minus 2 mean on the graph? And what is C1 on the graph? The vertical plane, you see it's shaded right here. This plane looks like part of a plane. Y equals 1 intersects the graph of z in the parabola z equals 2 minus x squared, and that's when y equals 1. The intersection between them is called C1. Now here's what I have. If y equals 1, this right here reduces to 4 minus x squared minus 2 times 1, which is 4 minus x squared minus 2. 4 and minus 2 will be 2. 2 minus x squared is the final answer. But, I mean, think about this. This is the x and z plane. X and z plane. So if you graph between z and x plane, 2 minus x squared, it's a parabola that opens down, because that acts like in lower math as my y, correct? We say it opens down. Shifted up 2 units. So it's a parabola right there, not the whole thing outside. It's a parabola down right there. But I got this by fixing y equals 1, which means I'm not supposed to be there on the plane of x, z. I'm supposed to be out of that plane, leveled with y equals 1. That's the parabola. It's not continued to the other side, but that is my parabola. That is my C1. So what is C1? It's the intersection of the paraboloid with a plane that is being called y equals 1. Imagine if you take this as a cake and you want to slice it, okay, at y equals 1. You just want to go back and forth with the x-axis, so x varies, but you're not going to move on the y, right or left, because now my y is kind of like right and left. It's not like the normal way when we look up and down, okay? So it's great concepts, not complicated, and it's very interesting. If you slow down and see it, it does make a lot of sense. Y equals 1, I'm to the right, if you call it that way, to the right. And that simplified this whole thing for me to a parabola. And I could see it. It's right there. The C1, if you continue, it's a parabola that opens down. Now, when you find the derivative with respect to x, because x is my variable, I'm going back and forth this way. I'm going with the x-axis, in other words. My x is fixed. Plug in 1, you get 2 minus 1 to the second. Sorry, that's the z-value. That's the z-value. Back here. F of x, y, derivative with respect to x is minus 2x. Plug in 1, you get minus 2. What does that minus 2 says? It's the slope of the tangent to this curve, C1, at 1, 1, meaning at 1, 1, 1. Because the z-value, when x is 1 and y is 1, up there, it's 1, 1, 1. I think that's good enough for this one. I have another one from the other point of view. Let's take care of it. Hopefully, after the second, we'll get more clues about what's happening. Here's the other way around. Now, y is changing and x is fixed. That means I'm gonna maybe go out this way on the x value and keep it 1. If I keep x equals 1 and I'm on the surface, I can't be here, I can't be here, I can't be here, I can't be here. I have to be tracing this line. Because as long as I am on this curve, I said, instead of line, on this curve, my x is 1, but my y changes, and my z changes. This plane is x equals 1. And it's all the way, but if you want to make a connection between x equals 1 as a plane and intersect it with my paraboloid, you're gonna get C2. Here we go. The curve C2 is in which the plane x equals 1 intersects the paraboloid is the parabola z equals, and you know that this is a parabola in 2-dimension zy plane. Zy plane, but it's not graphed on the zy plane. It's outside, sticking towards this way when x equals 1 built. That's why it's kind of like out of the wall, if you want to call it. So that is C2. It's a parabola. I could see that it's a parabola that opens down, shifted up 3 units. So if you graph it back, you're going to see it crosses the z-axis at 3, not at 4, down somewhere here. Alright? The slope of the tangent line T2 at 1, 1, 1 is, find the derivative and plug in 1, 1, you get negative 4. This is how you find the derivative. fxy equals 4 minus x squared minus 2y squared. That's my whole thing, the paraboloid. The derivative with respect to y will be, this is going to be 0, this is going to be 0, because we are treating x as a constant. The derivative of minus 2y to the second will be minus 4y. At 1, 1, I'm just going to have to plug in 1 for y, and it's negative 4. It looks like this one is steeper going down, because I told you it's narrower with the y, because it goes, you see the 2 right here, narrower with the y compared to with the x. So it's steeper at the same point going down. So if you're surfing on this curve, you're going down faster at this point compared to the original graph that I had it going with having y being fixed when it was called C1 and T1. Here's an example. It's a quick one, just practicing partial derivatives. Sine x over 1 plus y. They want you to find df dx and df dy. We're going to use the chain rule. With respect to x, I'm going to go sine, make it cosine of this angle. Go inside and find the derivative of this with respect to x, as I'm saying. The derivative of this with respect to x, imagine this like x over 5. It's going to be just 1 over 5. And that's what I have. On the other side, we have df dy. With respect to y, sine is cosine. The angle is the same. We're going to go inside and find the derivative of this with respect to y. We're going to use the quotient rule. And that's what I have. Alright. Implicit differentiation. Implicit differentiation. That's when you have everything everywhere and you want to find dz dx. So z is right there and z is right there. So to reach out to it, I don't have it clearly stated as z equal. So we call this implicit differentiation. We're going to find dz dx and we're going to find dz dy. When you find it with respect to x, that's the first one, we're going to treat y as a constant. So this is x cubed, y to the third, z to the third, and 6xyz equals 1. For 6xyz, we're going to use the product rule. For x cubed, finding derivative with respect to x will give me 3x to the second. Y cancels. It's a constant. We are treating y as a constant. This right here, z cubed, will give me 3z to the second. Pay attention to this. And that's why I'm trying to let you focus and see it. Sometimes students, they write 3z to the second and move on. No, you have to use the chain rule because we're going after the z dx. We're not doing the x dx or dy dx. So that's my main function name, z. So dz dx has to be displayed. Just applying the product rule right here, I end up with 6yz plus 6xy dz dx. You could take 6xy as one piece and z as the second piece. When you take the derivative of 6xy as a product of z, derivative of z with respect to x will be dz dx times this as is, which is 6xy. Kind of lengthy to say it. It's a product rule. And this is the product of the other part, like, derivative of this is a constant. Now here, derivative of this, and this is a constant. Derivative, I have 6yz, because we're going after x, by the way. Derivative of 6xy with respect to x will be 6y. And z will be treated as a constant because, like u times v prime plus v times u prime. So that should do it. And I think it's good enough. Now solve for dz dx. dz dx, dz dx. I need those to be together. Move this to the other side. Move this to the other side, by the way. I have minus 3x to the second to the other side. 6yz to the other side, then divide by, after you factor out the z dx from this here and this right here, skipping the algebra steps to save you some time and show you more. Here's the answer. Let's go after the second part. We're going to find the derivative of this with respect to y. The main focus here is not the algebra. It's how you do it, being careful. As you can see, I'm trying to box things in different colors. Now with respect to y, this is a 0 to me because that's a constant. We'll treat x as a constant. The derivative of this with respect to y will be 3y to the second. Derivative of this with respect to y is not 0. Z is a function of x and y. So that's what I'm saying. You have to be careful. 3z to the second times dz dy. Product rule again. Just be careful, practice, and if you need help, let me know. You could leave me a comment below, you could reach me out in class, and we'll take care of it. Rearrange. The focus is on the z dy. Move this to the other side, as you could see. Move this one to the other side, as you could see. Factor this out, and those will be inside parentheses. Divide by them, and you get this. It looks like everything divides by 3, so let's do that. And that's the final answer. That should do it. I'm trying my best not to go over 30 minutes, and I think I made it this time with a kind of a lengthy concept. Thank you for watching, and I'll see you next time. Thank you for watching. Don't forget to hit the like button, subscribe to see some more, and I'll see you in the next one.